And we'll set up from the current slide. Okay, now let's talk about ending the term, okay? I put the test out on Blackboard, but then everybody wants a copy. Do you want a copy too? Okay. And I have the test made out for your test 4, which we're doing in chapter 4 right now. And I was typing that when, I can't remember how many interruptions I've had since I got here this morning. The last being my boss when he called, and I could not finish typing the test. I think I typed question 6 out of 10. So I was going to put it out there too, but if y'all don't want it on Blackboard, I can have copies made by this. We ran into the same problem as before. I can bring a copy. Are you going to be on Birmingham campus Friday? Oh, but you may not be off work. Okay. It'll be on Blackboard today, and if you need a copy, I'll try to get a copy. Because you can't access Blackboard either, or can you go to...
I just don't have a computer without traveling.
Okay. Well, okay. I'm pretty sure the STEM lab on Birmingham campus has computers and printers. I don't know what the hours that it's open, but I know you can use that one. And I know there's got to be some other places too. Are you available Friday?
No, we don't have Friday.
Home or away?
It's home, but it's a double header.
Okay. Do you think you can have it done by then? What time do you have to be at the game?
I mean, I can have it done tonight. I just go somewhere.
Okay.
I can email it to you tonight.
Okay. Well, if you want to email it, I'll accept it because Anil did email it. So yeah, if you'll email it to me, and if it's dated by today, you don't lose any points. If it's dated tomorrow or later, you start losing points. Okay. All right. Well, test 4, I'll put out there just like I did test 3. If you need a copy, come by to see me, and I'll get you a copy of it. But I'll make at the end of the class. Let me know how many need copies, and I will. So far, it's all 6, but more may come in, and I will make as many copies as you need and bring them back up here before you leave. Okay. What else? Have you done the student course evaluations? Yes? If not, please do those. Please do those. Okay? What else? Okay. Everything has to be in, I'm sorry about this one. Everything has to be in by, okay, let's say this a different way. Technically, you have next week to turn in your test. You got test 3 and test 4, okay? And they're both short, okay? I think you can do them fairly quickly. But I'm not going to be on campus Thursday or Friday of next week. They've scheduled us a trip down to Tallahassee, a worthless, wasted trip. So that's when I need to be grading finals and stuff, and I'll be down in Tallahassee. But if you can get it to me by Wednesday, I can take it with me and be grading it while I'm down there. Okay? If you can't, turn it in, slide it under my door either Thursday or Friday, and I'll be back on Monday, and I'll pick them all up then and get them graded Monday. I can't remember if it's Monday or Tuesday the grades are due in, but they're just going to have to wait. They had me out of town. I can't, do it all. So I'll try to get everything graded Monday morning and the grades in. So is that okay with everybody? Okay? All right. I'm going to be out of town Thursday and Friday of next week. They scheduled for us, a bunch of us, to go down to Tallahassee. Worthless trip, in my opinion, but they're requiring me to go. So we'll be leaving Thursday morning around 10 from the Birmingham campus, I'm pretty sure. So I will be over there. If you want to turn it in to me then, I can take it, either of your tests. I'll be on this campus Monday, Tuesday, and Wednesday of next week. I'll be on Birmingham campus, I think up until 10 o'clock on Thursday morning. And then after that, we'll be gone. I'll be gone Friday. We're going to be down there. We'll be getting back really late on Friday, and that'll be on the Birmingham campus again. So if you can get me one test, that would be great. Monday, Tuesday, or Wednesday, or Thursday morning on the Birmingham campus. Does everybody know where my office is on the Birmingham campus? Dr. Pruitt's office? You know where that is? Okay, yeah. I'm in the copy room behind the secretary's desk. And I'll be there Thursday morning up until around 10, or whenever we leave, and I think they said it would be 10. Then, I'll be back in my office here on Monday. So if you can't get it to me by 10 o'clock Thursday on the Birmingham campus, slide it under my door here on this campus, either later on Thursday or Friday. If you can get me anything sooner, get it to me as soon as you can. One test or two or whatever. But if you can't, then turn the others in, slide it under my door on Thursday or Friday, and I will pick it up Monday morning and get it place graded. The final is your last test, chapter 4 test, the one that I'm putting on Blackboard. I was typing it when I can't remember, 2 or 3 phone calls, and students and maybe one faculty member came in while I was trying to type. And so I got through question 6, but I didn't get 7 through 10 typed. So I'll have those done hopefully shortly after class is over. Okay. And I'll put it on Blackboard, and I'll make you copies of test 3. If you need a copy of test 4, just come see me as soon as you can, and I'll make a copy of that for you as well. Okay. Anything else? Please see the suite of course evaluations. All right. We were going to do example 8. I think that's we got 2 examples left, 8 and 9. So let's do this. And we had just talked about finding a particular solution. And to keep from going over that again, let's just do it with this. Find the general solution of f prime of x is equal to 1 over x squared for any x greater than 0. Of course, x can't be equal to 0, so we're going to do any x greater than 0. And then find the particular solution that satisfied the initial condition that f of 1 is equal to 0. All right, where do we begin? How do you find the general solution? If this is helpful, let me write it this way. Let me get my pen color changed. Okay. Let's rewrite this f prime as df dx. Is that okay? Doesn't that mean the same thing? Okay. Is equal to 1 over x squared. Okay. Of course, as long as x is greater than 0. Okay. Now, write this in differential form. What would that be? On the left would be, y'all remember differential form? Okay. Now this isn't what you're doing, of course, but it sure looks like it is. Multiply both sides by dx. That's what it looks like you're doing. Now, df dx is not a fraction, so you can't technically do it, but that's exactly what it looks like. On the left, you have df. On the right, you have 1 over x squared dx. Right? Now, integrate both sides. Okay? Now, the integral of df is just, antiderivative of df is just f. Right? Now, before I would try to do the antiderivative of this, guess what I would do? Rewrite it. And why would you rewrite that? Say again? Okay, and how would that read then? Negative 2 dx. Perfect. Okay, now let's integrate that. or take the antiderivative of that. And that would be what?
X to the -3rd.
You're taking a derivative. -1. Remember, you add 1 when you're doing antiderivatives. Add 1 to the exponent, x to the -1 over -1, which basically just changes the sign, right? Dividing by -1 just changes the sign, right? And then you have one other thing to do. Plus c. Okay, so here is your general solution. That's what they asked for first. F of x is equal to minus x to the -1. Now, do you want to go back and put it 1 over? You can if you want to. That might be easier to do your work with. You want an exponential form when you're integrating, but I think when you're evaluating, it's probably easier to do 1 over x, right? Plus c. Say again? Okay. Now, there's your general solution. What's your particular solution? Plug it in, plug it in. F of 1 is equal to what? I don't think so. Yeah, it is equal to 0. You're right. Okay, we'll put equals 0. And what's that if you plug in a 1 here? -1 over 1, which is -1, right? Plus c. Plus c, right? All right. There you have an equation in c. Guess what c is? 1. Add 1 to both sides, and you get c is equal to 1. Now plug that back into your general solution, and your f of x is equal to -1 over x plus 1. Okay? Now, if you wanted to check this answer, you can take a derivative of it. Now I'd rewrite this as x to the -1, okay? Minus x to the -1. Take a derivative of that, and it would be plus x to the -2. That's exactly where we started, okay? Here, okay? Or here, okay? And then the other thing, if you plug in here, f of 1, that would be -1 plus 1. Sure enough, it's equal. So, it checks. There's your particular solution with the c in it. Here's your general, this is the general solution with the c in it. Particular solution when you evaluate what c is. Does that make sense? Okay. Now, let's see how they did it. I'll erase. Can I erase that? Y'all got it? Got it? Okay. Okay. They started with to find the general solution, integrate to obtain. I didn't tell you how to integrate, but write it in differential form and then integrate. And when you integrate a df, you get f. Okay. That's the antiderivative of df is f. Okay. And then antiderivative of that you get. You rewrite it as integral of x to the -2 dx, just like you did. And that becomes negative, and they actually worked it out the same way. X to the -1 over -1 plus c, which is just merely -1 over x plus c. And this, again, reminding yourself, x is always greater than 0. That's your general solution. The particular solution is plug in at 1 for x, and you get -1 over 1 plus c, and that's equal to 0 because your particular solution initial condition was alpha 1 is 0. And that gives you -1 plus c is 0. C is equal to 1. So what you do is plug that back in to this, and your particular for your general solution, f of x equals -1 over x, and instead of plus c, you put plus 1. There it is. Now here's your family of curves. This is just the ones with c equal integers. You know, they just all look like this. They're all, you know, you might say parallel with each other, though that's not very common. But here we have when it's equal to 1. Yeah. Okay. And that's the curve that we're talking about. particular solution satisfies that condition, that f of 1 is equal to 0. So f of 1 equals 0. Got it. Okay, any questions on that? That is the last they show. Let's do example 9, that they don't show. Solving a vertical motion problem. Okay? Why in the world did we say this, show all the sort of easy ones in the example that an application they don't show? A ball is thrown upward with an initial velocity of 64 feet per second from an initial height of 80 feet. Okay? We'll assume the acceleration is the acceleration due to gravity of negative 32 feet per second, or feet per second squared. Okay? Find the position of the position function giving the height s as a function of time t. Okay? Now, there is no, they don't indicate there's any x displacement. This is indicating throwing it straight upward. Okay? So that's the initial velocity straight up is 64 feet per second from an initial height of 80 feet. Now, they do, I'll ask you to look at their graph in the book. They show this. I'm going to do a slightly different one here. Okay? Here's a person, say, on the cliff. Okay? And this cliff is 80 feet high. Because they say from an initial position of 80 feet. Okay? Okay? The person throws the ball straight up. Almost straight up. Just enough so that it can miss the edge of the cliff on its way down. Almost straight up. They're right at the edge. Okay? And the initial velocity, VI, is 64 feet per second. 64 feet per second. But all along the way, the acceleration is minus 32 feet per second squared. Okay? Now, find the position function giving the height s as a function of time t. Okay? Now, I'm trying to remember how much of this we've done before, and we haven't. They're not assuming you know anything, okay? Except one thing. They say under A, it says, recall that A of t is equal to s double prime of t. I hope you remember that. Your acceleration is a second derivative of your displacement. Okay? So that's where we're going to start from. But let's write down the other things we've got here. S of 0, that's your displacement at time t equals 0. You are, and the ball is 80 feet up. So that's 80. And you have V at time 0, that's your velocity at time 0, right when you release it, is 60 feet per second. Now, they're not putting units in, so I won't either, though it's probably a good idea to. And then your acceleration at every time is negative 32 feet per second. Well, I wrote that in, so let me write these others in. 2 feet per second, and this is feet. Okay? Now, like I said, what they expect you to remember is that acceleration is equal to S double prime. Okay? Now, yeah, we did higher order derivatives. This is d2s per dt squared is equal to A. Does that make sense? All right. Now I'm going to split this up into a little bit more usable term. D, my D didn't write, there it is. D of ds dt, d by dt of ds dt, that's equal to A. That's where we got the d2s dt squared. I don't know if you remember that, right? All right, so what we're going to do here is write this part in differential form. By the way, our A is negative 32, right? And here's Elijah. Okay, before you leave today, Elijah, I did return some papers earlier, so pick those up before you go. I just got to find you now. There you are. Okay. I made several announcements. Let me go through them quickly. Have you done student course evaluations? Not yet. Okay, please do those before you leave for the term. But sooner the better, because you're less likely to forget it. If you wait till the very end, when I was an undergraduate, the brain shut down as soon as that last final was over, and I didn't think about another thing. So don't let that happen. Do your student course evaluation. Number 2, I put test 3 out on Blackboard, but so far no one has made a copy. Do you need a copy? You already got it. Okay. Huh?
I can make a copy.
You can. You don't want me to make one for you. Okay. All right. Third point, I was interrupted so many times this morning when I was in the office. I remember 2 more phone calls. And it was a total disaster. I came so close to finishing typing it up, but I don't have it finished typed. So as soon as I get out of this class, I'll finish typing the test 4, which is your final exam, and that will be, I'll put it on Blackboard also. If you need a copy, come see me. And then these are all due anytime next week, but if you get it to me by one or both of them by Wednesday, on this campus, I'll be here till, get it to me. I'll be here till 6 o'clock on Wednesday on this campus. Then Thursday morning, I'll be on the Birmingham campus. This is next week, finals week, until around 10. And then a bunch of us have been told we have to go to Tallahassee for some sort of a deal going on. And we've got to be there. We're going to be leaving around 10. So if you get it to me on this campus by 6 o'clock on Wednesday, Birmingham campus by 10 o'clock on Thursday morning, then I can be grading things while I'm down in Tallahassee. And then if you get it to me sooner, I may even get it graded before I leave for Tallahassee. But and your research papers too, I don't remember if you've done yours yet. Those are due in today, or after today they start losing points. So please get those to me. And then if you can't get it to me by 10 o'clock Thursday morning on Birmingham campus, you can bring it and leave it under my door here Thursday or Friday. I'll get them Monday when I come in to campus and get them graded then. So please try to get your test 3 and test 4 in. You can turn in one before you turn in the other. Do as much as you can, as frequently as you can. All right, so this is 32 minus 32 feet per second squared. Now, I'll leave off the units now. Okay, so we're going to write this in differential form, and that would be d of ds dt is equal to minus 32 dt. Writing this part on the left, that part on the right, okay, with the differential over there. That's supposed to be minus 32. I don't know where the 3 went, okay. Oh, I see where it went. Just part of it wrote. Okay, I'll get all of it right this time, I hope. Okay, now we can integrate both sides of this, and that would be the d's and the integral go out, and you have ds dt is equal to, and what's the antiderivative of negative 32 dt? Negative 32t plus c, right? Don't forget your plus c. Now, what is your ds dt? This is your velocity. ds dt. That's the other thing you have to remember. That is what your velocity is. First derivative of your displacement is your velocity. Second derivative is your acceleration. Well, we know what the speed is at time t equals 0. It's 64. So basically this tells us that ds dt is equal to 64 when t is equal to 0. So that would be, well, when t is 0, the first term is 0, that's equal to c. So 64 is c. So now we have, I'm running out of room, ds dt is equal to minus 32t plus 64. And guess what we do next? Not yet. This is now in the integration. You integrate. Or write it in differential form. ds is equal to minus 32t plus 64 dt. Right? That's in differential form. Integrate both sides. Okay? And this just gives you s of t. And here's Chaston. Alright. Y'all are going to hear this over and over. Sorry about this, but I want to make sure everybody hears. Number one, have you done student course evaluations? Yes, good. Okay, number two. I did put test 3 out on Blackboard, but a lot of people said they haven't printed it yet. Could I print them a copy? I'll do that right after class, so let me know if you need a copy of test 3. I was in the process of typing test 4 when I had a trove of phone calls and people coming by my office and stuff, so I wound up just short of getting it typed. I'll be typing on it as soon as we get out of class today, and then I'll put it on Blackboard. If you need a copy of that, come see me today, tomorrow. Would be best today or tomorrow. I can do it on Birmingham campus on Friday if you want to come see me then. Okay. Now, when do you need, research papers are due today. So if you haven't got it turned in, get it to me today. After today, you start losing points, but it's better to lose points than to get a 0, because you can't drop the research paper. Okay? So get that to me as soon as possible. And when are the other things due? Test 3 and by the way, I did pass out test 1 and 2, so get yours before you leave today. And let's see, the other thing. Please don't let anyone else see your test, because there are some people in the class who I haven't seen in forever, and I don't know if they're coming back. One said he probably is going to withdraw. I hope he's done so, because it's getting awfully close. If it's not already passed it the last day you could. The others, some of them have turned in work late, so please don't let anyone see it, because they may see your correct answers that I put on your test and then cheapen your grade by filling in their stuff. So please get that done. Okay, when can you get it back to me? I'll be in here on Bessemer campus Monday through Wednesday of next week. I'm giving a final Tuesday morning, and I'm giving a final probably Wednesday afternoon. But except for that, I'll take that back. Giving a final Tuesday morning, having a class with a final Tuesday afternoon, and then giving another final Wednesday afternoon. And, back up again. I've got a class Monday afternoon, 4 o'clock on the Birmingham campus. Then a final Tuesday morning at 8. A class with final 1:15 until they finish Tuesday afternoon. A final Wednesday afternoon at 2. And then, so I'll be on Bessemer campus Monday through Wednesday, and then on Birmingham campus Thursday morning from 7:45 till 10. And at 10 we're leaving for Tallahassee, and then we'll be back late Friday. So if you can't get me your test by Wednesday evening on this campus, 6 o'clock Wednesday evening on this campus, or 10 o'clock Thursday morning on the Birmingham campus, then bring them to this campus either Thursday or Friday, slide it under my door, office door 265, and I'll pick them up Monday morning when I come in and try to get them graded in a hurry. Okay? Make sense? What's that? We don't. Monday starts finals. It's just I've got 2 mini-term classes, and they have class one on Monday and one on Tuesday of next week. Full-term classes don't have classes next week. Only second mini-terms have classes. That's why I had to break it up. I have some classes and some finals. So it's sort of nuts, but I'll work it all out. Okay. Where we left off in this problem, and what I'm going to do is erase just so I can have more room to write. Okay? Here's what we were down to. And it's not erasing very well. This is very slow erasing. Okay. It's picking up speed now. Okay? So, here's what we were down to. S, or ds, is equal to minus 32 plus 64 dt. Okay? Now, integrate both sides of this, and you get s. S is a function of t is equal to, what's the antiderivative of negative 32t? Got it. And the antiderivative of 64 dt. 64t. One more little thing. Plus c. We got it. Okay? Now, that's s of t. Let's do s of 0. Well, s of 0 we have up here is 80 feet. So this will be 80. I won't put the units in. And that's equal to, well, when I put a 0 in for t squared, that goes away. Put a 0 in for t, that goes away. And you're left with c is equal to 80. So now your final solution, your particular solution is s of t. I think that's what they're asking for. Find the position function giving the height s as a function of time t. S of t is equal to minus 32 t squared. No, I'm sorry. 32 divided by 2 is 16. Let's write it as minus 16. Okay. Minus 16 t squared plus 64t plus 80. There it is. Particular solution for these initial conditions. Okay? Any questions on that? All right. And you see s of t is minus 16t squared plus 64t plus 80. Then the next thing is, when does the ball, that's the A part, when does the ball hit the ground? What's going to be its height when it hits the ground? 0. Okay? So what we'll do then, and I'm going to erase some more stuff so I can write. Hope this isn't too confusing. Okay. And this is the easiest part of the problems, unless you've forgotten your algebra. So 0 is equal to minus 16 t squared plus 64t plus 80. Okay? Now, how would you go about solving something like that? Factor! I was just going to ask, what's the F word? Okay. What's the first thing you would factor? How? What would be your first step in factoring? What you always want to factor out first. Yes, greatest common factor. And take the minus sign with it. I don't like leading off with a minus sign. So let's factor out a minus 16. And what do you have left in the first term? T squared. And you factored out a minus, so it's going to change that sign to a minus. 16 will go into 64 how many times? 4t minus, because you factor out the minus sign. 16 will go into 80 how many times? 5. Okay. Now, what we're going to do with that minus 16? Divide it out. Okay. And for some reason my pen is doing all sorts of squirrely things. So let's see if I can erase some of the squirrely things and get it to do right. Okay? And that just merely goes to 0. 0 is equal to t squared minus 4t minus 5. Okay? Now, what do you do with that part? As in, continue factoring, and how does that factor? Okay? First term is going to be t times t. Look at the sign of the last term. What is that? Negative. What does that tell you about these two signs? Opposite. One plus and one minus. I don't care which order. And what two numbers can you use that when you multiply gets minus 5, you add and you get minus 4? 1 and 5. Okay, in that order too, right? And this is equal to 0. Now what does that show you or tell you or produce for you? Okay, if we're doing a derivative, yes. We're not doing a derivative, we're just finding the solutions. And what you do, the only way a product of two entities can multiply to be 0 is if one of them is equal to 0, or both. Okay, so either t plus 1 is equal to 0, or, y'all did this a long time ago, right? T minus 5 is equal to 0. Okay? Now, what does the first give you? If you solve for t. Yes, t is equal to negative 1, and t is measured in seconds. Okay? Now, how many times do we have negative seconds? As in, never. No Back to the Future here. Okay? Over here you get 5 seconds. That seems like when it hits the ground. Well, where did that negative 1 second come from? That's saying if he had thrown the ball from ground level, it would have been down here 1 second before he released it up here. Okay, we'll buy that. Okay. But we're not doing that. He threw it here at t equals 0. There wasn't any minus 1 second. So t equals 5 seconds is your answer. What? Oh, yeah, okay. I thought it said negative 1.5. I said, no way. Okay. All right. That finishes 4.1. All right. Homework exercises here. Do 5. This is on calcchat.com. Either 7 or 9. They're both at calcchat.com. The 7's at calcview.com. Any of the, either 11 or 13. They're both at calcchat. 13's at calcview. Any of the odds 15 to 35, they're all at calcchat. 15's at calcview. Any of the odds 37 to 43, they're all at calcchat. 37's at calcview. And then they're doing something we haven't done in class, and you can certainly take a look at it, but don't sweat it. I'm not going to give you these on a test or something. But you will see this again if you ever take differential equations. Okay? So you can look at 45 if you choose. You can do 47, that's a calcchat, and probably 45 is a calcchat too. 49 probably is a calcchat. You can certainly give that a shot if you would like. 51 should be a calcchat. You can give that a shot if you like as well. 53 and 55, you can give either one of those a shot. They're both a calcchat. They should be. Same with 57 and 59. It's a lot like the problem we just did, a little bit differently. That's 57 or 59. And then 61 is another vertical motion problem. You can do that if you'd like. Okay? Very pretty picture of Grand Canyon there, but I'll let you decide whether you want to proceed with that or not. Tyler? Okay. So, need to go back through everything again just to make sure everybody gets to hear it. Number one, have you done student course evaluation? Have you? No. You know how to do it. Okay, did everybody see the email? Okay, it didn't talk about student course evaluation. It's on voting for SGA officers or something like that. That's the one with the link. Okay, so please do your student course evaluations. Did you get your test 3? I put it on Blackboard. You did? Okay. If you want a hard copy, I'll make one after class. Several people have requested it, so I'll make copies if you don't want to print yours online. Okay, so let me know. That'll be at the end of class. I came that close to finishing typing out test 4, but I had so many interruptions, I didn't get it finished. So as soon as class is over, I'll finish typing that out, and I'll put that on Blackboard as well. They're under content, okay? I thought I'd put them under announcements, but it's harder to get them there. I put it under content. Probably going to be at the end of content. It's a pretty long content file. Okay? Now, your research paper was due today. If you get it to me before the end of the day, you don't lose any points. If you don't, you'll start losing points after today. Okay? Okay? Then, well, how about the other things? The remaining. Oh, and by the way, your earlier test, I think I was grading on yours last night, and I hate to say this, I just fell asleep on the sofa. Sorry. It was just, I'll see what I've got, and I'll return anything I've got to you. It may have been one of the other students who turned in some stuff. Okay. This treatment, I'm still fatigued like crazy, especially at the end of the day. I'm making it through the day better, but boy, at the end of the day, I'm white slipped. Okay, but anyway, I'll put your test 4 out on Blackboard. Now, when do you get test 3 or 4 into me? Anytime next week. Let me give you this. If you can get it to me Monday through Thursday, I'll be on Monday through Wednesday, I'll be on this campus almost straight through Monday through Wednesday. Couple little exceptions. I won't always be in my office. For instance, Monday evening, I'll be on the Birmingham campus teaching a class from 4 to 6. But you don't want to try to chase me down there, just leave it under my door. Tuesday morning, I've got a final in this room from 8 to 10. 8 to 9:50, almost 10 o'clock. Okay? Tuesday afternoon, I've got a class from 1:15 until they finish their final, and that'll be in this room. After that, I'll be down in my office. Wednesday, I've got a final 2 o'clock in the afternoon, 2 to 4, until they finish, okay? So Monday through Wednesday, I'll be primarily on this campus. If you can't get me one or both of them by Wednesday evening, if you want to deliver one to the Birmingham campus before 10 o'clock Thursday morning, I'll be there until 10 o'clock Thursday morning. Then a bunch of us have been told we have to go to Tallahassee, so we'll be leaving by bus to go to Tallahassee, the van, the campus van, and we'll be down there through late Friday. So I won't be back. So what you'll need to do, if you can't get it to me by Thursday at 10 on the Birmingham campus, put it under my door on this campus, Thursday or Friday. And then I'll pick it up Monday morning when I get back and get them graded then. Make sense? All right. Now, we're going over homework exercises on page 257. Okay, I just said there's a pretty picture of Grand Canyon there. There's a lunar gravity problem, number 63. You can do that if you'd like. It should be at Calc Chat. Either 65 or 67, they should be at Calc Chat. 69 or 71, those are similar to the problems we did just now. You can do either one of those or both there at Calc Chat. Then there's some true-false, 73 to 77. You can do those if you'd like. They're good to check on the concepts. 79 is a proof. That's up to you. All right. Any questions? Chapter 4. 4.1, sorry. Now, I'm beginning to realize that I've made the test too long, okay? I'm not going to go back and change it, so I might just stop the test where it is at 6 questions, and that'll be it for the final, okay? Because I don't think we're going to get some in chapter 4.2 done, but I don't think we're going to finish it. So let's move on to 4.2 if there are no questions on 4.1. Okay. PowerPoint has been slow today. All right. We're still in Chapter 4, Integration, and we're moving on to 4.2, which is Area, which is one of the first things that we usually do with integrals, is calculate area. So we're first going to start with a sigma notation to write and evaluate a sum. Have y'all dealt with sigma notation before? It's pretty simple, but it just looks complicated. It's not. We'll understand the concept of area. Of course we will, okay? Oops. We'll approximate the area of a plane region, and then we'll find the area using limits. Yay! We missed our limits, haven't we? Let's start with sigma notation. This section begins by introducing a concise notation for sums. This notation is called sigma notation because it uses the uppercase Greek letters. The Greek alphabet has uppercase and lowercase like we do, and their uppercase letter sigma, which corresponds to our S, is that notation there. That's the sigma. I don't know if you remember the show on television, a pretty decent show called Numbers, where the mathematician was the hero always. I don't know if you remember that. They always wrote the E as if it was the sigma. That didn't make sense. It should have been the S as a sigma for numbers, but they put the E in there, which is a little bizarre. Okay, never mind. Sigma notation is the sum of n terms. If you had a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, up to a sub n, and you wanted to write that in shorthand notation rather than a1 plus a2 plus a3 plus a4 plus a5 up to plus a10, that would be longhand notation. The shorthand, and by the way, mathematicians are usually what? A little lazy. Always trying to find a simpler way to write it. Here's how you'd write it. It'd be the sum, the sigma, from I equal 1 to n of a sub I. And if you think about that, that would be, starting with I equal 1, it would be a sub 1 plus, because it's a sum, a sub 2 plus a sub 3 plus a sub 4 plus a sub 5, up to I equal n, and you stop. So that's what it means. It's just a shorthand way of writing a long sum, where I is called the index of summation, and a sub I is the ith term in the sum, and the upper and lower bounds of summation are n, that's the last one, and 1 is the first one. You could have started from I equals 17 to n equals 40, okay? That would be a sub 17 plus a sub 18 plus a sub 19, and go all the way to a sub 40. So it's pretty flexible notation, okay? Most of the time we start either at 0 or 1, but not always. Okay, so let's do a few. Here is sigma, and you're summing I when I goes from 1 to 6. So what would that be? First one would be 1 plus 2 plus, and you add them up. Easy way to add, by the way. 7 plus 7 is 14, plus 7 is 21. Okay. Gauss, I think, did that when he was in first grade, or something like that. His math teacher was mad at the class and wanted them to be quiet and have some quiet time for himself. So he said, write down the numbers 1 through 100 and add them up, and that's your classwork today. He thought that would keep him busy for a few hours. Gal sitting in the class immediately saw he started 1 plus 100 is 101, 2 plus 99 is 101, 3 plus, and then multiplied and had the answer in just a few minutes. And the teacher was really bad, you know, but easy way to do something like that. Okay, I didn't come up with it, Gauss did. All right, how about this one? Summation I equals 0 to 5 of I plus 1. What would be the first one? 0 plus 1 is 1. 2 plus 3 plus 4 plus 5 plus 6. Yes, you have to go all the way to 6 because I goes from 0 to 5, and the last one would be 5 plus 1 is 6. And then that's the same thing as we had before, so we don't have to go through that. 21. Okay? How about this one? A little more complicated. The summation from j equals 3 to 7 of j squared. Where would you start? 3 squared plus 4 squared plus. You got it. Okay? I'm not going to do that in my head. Okay? And they're not doing it either. So that would be 9 plus 16 plus 25 plus 36 plus 49. Use a calculator. I don't know. Whatever. That's what sigma notation is. Pretty simple stuff. Okay? How about this one? The summation of j going from 1 to 5 of 1 over the square root of j. So that would be 1 over the square root of 1, 1 over the square root of 2, 1 over the square root of 3, plus 1 over the square root of 4, plus 1 over the square root of 5. I'm not about to do that in my head either, okay? That would be purely miserable. This would be 1 plus 1/2. I can get those done. And the rest of them, never mind. Okay. That's how you do sigma notation. Any questions on that? There's a couple more. Let's do E. Okay. The summation from k equal 1 to n of 1 over n times k squared plus 1. Well, whatever your upper limit is, that's going to be your denominator. That's fixed. It's not varying. The k is the thing that varies. So what would that be? 1 over n times, you can just do them all. 1 plus 1 is, well, 1 squared plus 1 is 2. And they're doing the 1 over n each time. I would have just bracketed off. I'm more lazy than they are. And that would be 2 squared plus 1 plus 1 over n times 3 squared plus 1 plus 1 over n times n squared plus 1. Now what I would have done would have bracketed off the 1 over n and then just had those sums in there. That would be perfectly legitimate too. Okay? There's no numerical answer to that. Okay? Not unless you knew what n was. And then let's see F. All right. The summation from I equal 1 to n of f sub x sub I, f of x sub I times delta x. That would be f of x sub 1 delta x plus f of x sub 2 delta x plus f of x sub 3 all the way up to f of x sub n delta x. Guess what? That's the one we're going to be using a lot. Okay? Now, and I'll tell you another guess what. Remember we said at the end we're going to take a limit. We're probably not going to get there, so I'm going to tell you now. If you take a limit of this, the summation becomes an integral. And it will go from 1 to n. Now that's a definite integral. We haven't got that yet. And here will be your f of x. And the delta x becomes a dx. So here's another way to approach integration. And this is doing areas under curves. Okay? So that's what we'll be doing. From parts A through and B, notice that the same sum can be represented in different ways using sigma notation. Yeah, that was fun, wasn't it? The properties of summation shown below can be derived from the associative and commutative properties of addition and the distributive property of addition over multiplication. And the first property, K is a constant, okay? So here's what we've got. This is what I was telling you we could do earlier, okay, with that 1 over n. So I is your counter, K is just some number, and n is the upper limit. So this, the summation of from I equal 1 to n of K a sub I, this K is doing nothing but multiplying by every term. So factor it out. Put the K out front, and then the summation of I equal 1 to n of a sub I. Now, I'm not going to write those out, you know what they would be, okay? Now, this one is the summation of a sum or a difference of two entities. Well, guess what? The summation of a sum or difference is the sum or difference of their summations, okay? So just like we've done in just about every other rule before, you can split it. We did it with differentiation, and we actually did it with integration. And this is doing the same thing as we did with integration. You just bring the sigma across, and it's the summation of a sum or a difference is the sum or difference of those summations. So, general rule. And it's almost common sense. Okay? The next theorem lists some useful formulas for sums of powers. Okay? Now, the summation from I equal 1 to n of C, what would that be? C plus C plus C plus C n times, wouldn't it be? And what's the shorthand way for doing that? N times C, multiply. C times n. Okay? That's what we did. If you add the same number over and over and over, that's multiplication. Okay? So that was pretty straightforward. How about this one? The summation of, this is one we've seen before, I equal 1 to n, that would be, now here, this is the one, they're just giving you this, okay? I don't know if there's an easy way to show you why that's true. Remember how we, that would be 1 plus 2 plus 3 plus 4 plus 5, and they're telling you that would be whatever your n is. Let's say it's 5. 5 times 6 would be 30, divided by 2 would be 15. We did 7. Remember we did 7? No, we did 6, right? Yeah, we did 6. Okay, let's do 6. 6 times 7, 42 divided by 2 is 21. That's what we got, wasn't it? Okay? So this is just a shorthand. Hey, there it works. Useful formulas for sums of powers. Okay? There's no power there, but it is. Here's a power. The summation of I squared when I is going from 1 to n. Okay? I'll get this one. N times n plus 1, that looks the same. But now we have times again 2n plus 1, rather than dividing by 2, dividing by 6. Am I expecting you to memorize these? No, I hate memorization. But just sort of file these away somewhere where you know you can look them up if you ever need them. Okay? How about this one? Summation of I cubed. I going from 1 to n. Well, strangely enough, it's just simply the square of number 2, isn't it? N squared over n plus 1 squared divided by 4, which is 2 squared. Okay? It would be fun if we had time to go back and derive these and see why they're true. No, we don't have time, and that would be a fairly lengthy, but probably pretty fun process. But these are 4 powers that you can always go back and use. Okay? Now, if you remember that, And also remember the previous one that when you add or multiply, you can use these powers in that too. So, and by the way, let me go back and say this, because you'll run into this in future math courses. These two rules here, properties here, basically tell you that summation is a linear process, because this is your scalar multiple and this is your sum and difference. And forever in math, you'll be talking about linear systems. This is a linear system. And most of the systems we will do it. So if you have something multiplied by k, but it looks like this other than that, pull the k out, and then you've got your solution. Or if you have something added, two or more of these added together with k's in there or different constants in there, split them up and use those linear rules, and you'll still have your solution. Might take a little work, but it won't be too bad. All right, let's see if I can sit down slowly. Goodness, my knee hurts. Okay, let's evaluate this. Where would you be? Oh, I've got to initiate my color again. Okay, how in the world would you do this? Evaluate the summation. Well, you tell me, what would be the first thing you would do to this? We're going to do it 4 times. One for n equal 100, 10, 100, 1,000, and 10,000. Okay, we got time to do that many, don't we? Adding all those up, yeah, that'll take us into next spring, I believe. Okay, unless we can find the shortcut, or 2, or 3. So what might we do? Notice the n is not part of the summation process. That's just a number. So let's do it first for 10. Okay? Well, since that's not part of what's being summed, pull it out. That linearization thing. 1 over n squared. And we're doing this for 10. So we'll come back. And then we have the summation n equal, I equal 1 to 10. Let's go and write in the 10. Okay? And what's 10 squared? 100. So let's just write 100 there, okay? And this will be I, okay? But then we can break that into plus the summation from I equal 1 to 10 of 1. Okay? Now, want to have a flashback? Let's flash back first here. See what I did, that k was 1 over n squared. So I pulled it on the outside. And then the second part, we had an I plus 1. And I split that into the summation of I plus summation of 1. Right? Got that? Okay. Then, we have that summation of 1 is going to be this. Summation of I is going to be this. And summation of 1 is going to be this. Got it? So the summation of I is n times n plus 1 over 2. And summation of c is just c times n. So what do we have here? 1 over 100 of, and this was 10 times 11 divided by 2, right? Plus 10. It was c times n. C was 1. 1 times n. 1 times 10 is 10. Okay? Well, this is 1 over 100 times 110, right? Divided by 2 plus 10, which would be 1 over 100 times 55 plus 10, which would be 1 over 100 times, this isn't coming out right, 65. Oh yeah, it is, that's fine. And that is 0.65. Right? All right. That 1 over 100 in front, that's what makes it a decimal number. Okay? And so that's going to be 0.65. Okay? make sure I haven't done something really stupid here. Yeah, 0.65. Got it. All right. That didn't take us that many days, did it? Even though we summed 10. Well, 100 is going to take us a lot longer, isn't it? That would be 1 over, what's 100 squared? 10,000. Okay. And then the rest of it's going to be pretty much the same. The summation from I equal 1 to 100 of I plus summation of I equal 1 to 100 of 1. Okay? 1 over 10,000 times. Now this one will be 100, right? Times 101, right? I could get my pen to write. Okay? Divided by 2. Plus 100. That's not that hard, is it? Okay? So this will be I'm running out of room. 1 over 10,000 times, that's 100, 10100, right? Divided by 2 plus 100. Okay? 1 over 10,000. With a calculator, it might go a little faster. Okay? And this will be 5050. Isn't it? Yeah. Plus 100. That would be 5150 divided by 10,000. So that would be 4 places, 5 places, 6 places. 0.500515. And sure enough, that's what they got there too. Okay? And you see 1,000 is not going to be that much worse. Okay? The only hard part is this, and it's not hard, that'll be 1,000 times 1,001. This is going to be 1, oh, wait, you got that to do too. What's 1,000 squared? A million, okay? So it's 1 over a million, and you have 1,000 times 1,001, and you figure out what that is, and then that would be 1,000 over there. That's the only part that takes a little bit of effort, maybe to get the millions, and you'll see, if you do that, that there is a limit, and you look in the book and you see it's getting closer and closer to 0.5. So guess what? The limit of all this is n goes to infinity would be 0.5. Wait, I did something wrong, didn't I? Oh, there were only 4 zeros there. That's 0.515. I'm sorry. I put 2 extra zeros there. 0.515. Okay? And then you keep going and it getting closer and closer to 0.5. So let's end my scratch here and see how they work it. Okay? I think they did the same thing, sure enough. They pulled out the 1 over n squared because that wasn't part of the summation. I mean, it was just a constant. Whatever your n was, that was a constant. So pull that out. Then split that into the summation of I and summation of 1. Okay? Nice. Okay? And then, here's your theorem 4.2. The summation of I is just n times n plus 1 over 2. And the summation of 1 is 1 times n, which is just n. Okay, and then here's your formula. And all you do from here is just plug in the different numbers. You don't have to go back and do all the things. Oh, well, actually, they did one more step here that I didn't do. Okay, they come up with a least common denominator here, 2. So this will be n times n plus 1 plus 2n all over 2. And well, this is n squared plus n plus 2n over 2. So that's n squared plus 3n over 2. Okay? So they did that step, n squared plus 3n over 2. Divide that by n squared. Hey, that's not going to be so bad, because that's going to be, well, let's see. Yeah. N squared will go into n squared 1 time. Okay. So it'd be 1 over 2 plus 3 over 2n, and then you can mess around with that, and it comes up n plus 3 over 2n. Now, I didn't do that, but you can do the math. It's not that hard, okay? This would be the same as, let's do it this way, n squared plus 3n over 2n squared, okay? And then divide, okay? And that would be factor out an n here. Get rid of that n and that n. That leaves you n plus 3 over 2n. Okay? And that's what we got. So that's not hard to do. And then just plug in your different n's. This is so much easier than the way I was doing it. 10 plus 3 over 20. And that would be 13 over 20. And that was your 0.65. Right? Okay, then we did 100 plus 3 over 200. That would be 103 over 200. Do that on the calculator. I bet you get 0.5105 or something like that. 515 or 05? Okay, all right, 515. Okay, and then 1,000 plus 3 will be 1,003 over 2,000. See what that gives you. 5015. Okay, and is it a million? What's the next one? Is it a million plus? No, 10,000. Okay, 10,003 divided by 20,000. Okay, I think you'll see if you just keep going with that, you're going to just add an extra 0 and move the 1 5 further out. That's getting closer and closer to 1 5. Okay. Now, this is another way of doing that. What we're doing is the limit as n goes to infinity of n plus 3 over 2n. Now, we've done things like that before, a long time passing, wasn't it? This one, this is definitely one I would break into the limit, if I could write, as n approaches infinity, of 1 over 2 plus 3 over 2n, right? Why is my pen so slow? Okay, because n over 2n is 1 over 2, plus 3 over 2n is 3 over 2n. And as n goes to infinity, that's 1/2. And as n goes to infinity, 3 over an extraordinarily big number is awfully close to 0. So that's 1 to 1/2. So that's actually the easier way to do it. The others work fine, but amazing, huh? All right. Yo! Let's see how they did it beyond this step. Okay? Next step here, note, now you can evaluate the sum by substituting appropriate values for n, and it just makes it so much easier than what we were doing, but we're getting the same answer. Okay? Yes?
How did they get the 3 in there?
How'd they get the 3 in? Up here at the very top, right? Is that what you're asking? Okay. From this step here, that'd be 1 over n squared times n plus 1 over 2 plus 2n over 2, right?
Oh, yeah.
Yeah, common denominator. And this would be n squared plus n plus 2n would be n squared plus 3n over 2. Factor out an n, and you have n plus 3 over 2n. Isn't that what I got? N squared plus, wait, yeah, n plus 3 over 2n. Okay, did that answer it? Okay, good deal. All right, area. In Euclidean geometry, the simplest of a plane region is a rectangle, right? I'd say even simpler than that would be a square, but a square is a rectangle. Although people often say that the formula for the area of a rectangle is A is equal to base times the height, it is actually more proper to say this is the definition of the area of a rectangle. From that definition, you can develop formulas for areas of many other plane regions. I know we don't have much time, but let's give it a shot here. For example, to determine the area of a triangle, you can form a rectangle whose area is exactly twice that of the triangle, and this is what you get. Now, I don't know if you realize this, but if this is your triangle, any old triangle you happen to have, this is your base, there's your height. Okay? Now, this dotted line, number one, tells you what the height is, but it also, if you flip that across here, the same area is right there, isn't it? Okay? That forms its own little rectangle. Do the same thing over here, flipping that over, and that doubles as that too. So this rectangle with the base times a height, exactly half that is a triangle, and that triangle is 1/2 the base times the height. Wow. Okay? Just from geometric means, this is how you get that result. Okay? Once you know how to find the area of a triangle, you can determine the area of any polygon by subdividing the polygon into triangular regions and then doing that same triangle again. So a parallelogram, where the angles could be anything, divide it into this triangle and that triangle, and then do your triangles. This is a hexagon, divide it into 6 triangles. Any polygon, just pick one, probably the biggest angle you've got here, and use that as the vertex, and then do the thing, this triangle plus that triangle plus that triangle. Okay? Now, there's a lot of work to it, but you got everything you need there, almost. Okay? So any shape you can do that way. Finding the areas of regions, we're out of time. I did want to say this, though. Finding the areas of regions other than polygons is difficult. The ancient Greeks were able to determine formulas for areas of some general regions, particularly those bounded by conic sections. And they actually called this method the exhaustion method. Okay? And the clearest description was given by Archimedes, and this is why I wanted to say this. Here's another potential paper topic. I'd say the first of the great mathematicians ever to live, Archimedes. Some may argue there's some other great ones before him, but man, he was incredible. Essentially, the method is a limiting process that he didn't know about limits yet, which area is squeezed between 2 polygons, one inscribed and the other circumscribed about the region. And he came up with one of the first fairly accurate areas of the circle. Because just like these polygons you saw back here, say this hexagon, he drew one circle inside the hexagon and then did a hexagon inside the circle and computed areas because he could compute each of these. And then he did it with octagons and decathlon, and he just kept doing bigger and bigger, and every time getting closer and closer, and one inside, one outside was getting closer to each other, average the two, and that gave you an estimate for the area of the circle. And he literally called it the method of exhaustion. He kept doing it until he got tired of calculating all those areas and said, that's close enough, I'll stop. That's what integration is. It's that reaching that method of exhaustion, coming up with an easy way to do it. And we'll pick up and go, but you see, you'll get the same form we did before. Any of you going to be here for the summer? Okay. If you are, we'll pick up from this point and go. And so you won't be missing anything. Now, before you go, okay, let me first do it for those people who came in late. Give your papers to you. And I hope all of you have turned in all your tests. Okay. Justin didn't make it in today. Nathan didn't. Elijah. Jeremy didn't make it in. Yeah, you already gave you yours. Tyler, had you already turned in yours? No, first you test? Yeah. Okay. So I was working on grading those. I just saw that. Okay. So you won't need it for the final, but if you want to get it. Okay. Test 2. Starting back over there. By the way, please don't show them to anybody because not everybody's turned in these. Elijah, have you turned in test 2? Okay, I need it in. How many of you need copies of the test? Okay. Count off for me. 3, 4, 5, 6, 7, 8. I guess you didn't. So let's go get 8 copies made. So take me just a few minutes. Save it. Oh, man. Feel like I've run a race and lost. Okay. What's that?
Running though.
What's that?
Just
Keep running. Okay. Oh, did you get new? Oh, okay. I'm sorry. You're the eighth one. Okay, good. Okay. I was afraid I'd imagined it wrong. Okay, take care.